In today's video, we will discuss quantum axioms. Quantum axioms are quite different from the classical mechanics axioms, and that makes the quantum systems very different from the classical systems. For any quantum system, there is a corresponding Hilbert space H on field C. Hilbert space H in our context will be finite dimensional spaces, and in that sense, it is any vector space of finite dimension with field C. Axiom 1 is that the state of the system is any unit vector phi belonging to the space H with norm equal to 1. Axiom 2 is if the system evolves from time t1 to time t2 and the corresponding states are represented by phi t1 and phi t2, then the two states are related by phi t2 is equal to u phi t1, where u is a unitary operator. And if the system is evolving in continuous time, it evolves as this differential equation IH d by dt phi t is equal to h phi t. This is Schrodinger equation. In this equation, this h bar is the Planck's constant, and this h is a unitary matrix, actually Hermitian matrix corresponding to the system, and this is called the Hamiltonian of the system. Solution of the Schrodinger equation is given by phi t2 is equal to exponential minus I h t2 minus t1 by h into phi t1 if the system, so these are the equations at time t2 and relating them to the system equation at time 1. Thus, in the context of the previous statement, this operator is the U operator that we gave earlier, and this is unitary when H is Hermitian. Any quantum system which is closed, which means that there is no interference from the environment, evolves in this way. And thus these Schrodinger equations explain the evolution of a quantum system. Axiom 3 is about measurements. The system state cannot be directly observed. The state at time t, phi t, that we have represented, it cannot be directly observed. So this is in contrast to the classical systems. In classical system, like particle or system of particles, we can at any time see its velocity, its position, and so on, which are the state of the system. And but in quantum system, you cannot directly observe it. If you observe it, then the system state gets disturbed. This seems like a strange axiom here. However, if you see, usually quantum systems are for very micro systems, like systems of electrons and photons. This is what they explain. And if you consider one qubit system, that could be made up of a single electron or single photon. And to observe the state of a single electron or a single photon, remember the instrument that we have either will use light or it will use electricity. Light is made of a lot of photons and the electricity is made of a lot of electrons. So to observe the state of one electron or one photon by a stream of photons or electrons will obviously disturb the state of the system. So seen in that light, this axiom looks very reasonable. Now, how do you make observations on the system? In quantum mechanics, you make observations via some linear operators MM. These are the operators on the Hilbert space H corresponding to the quantum system. And these linear operators MM are such that if you take MM star, this is the adjoint of mm. So take mm star, mm, sum over all these operators that we have taken here. And if these are n operators, n is equal to 1 to n, that summation should be equal to identity. So this is the condition we put if we want to make measurements with respect to linear operators of a quantum system. If the system is in state phi, then the outcome will be m, which occurs with probability pm, and that is given by inner product of phi, mm star, mm, inner product with phi. So the number of observations corresponding to measurements here will also be equal to n, the number of operators here. And for output m, pm is the probability. After the measurement of the quantum system, this system state has changed. The system has been disturbed. Whatever the system before was, now after the measurement, if the outcome is m of the measurement, then the system state after the measurement is mm phi, and it's normalized by its norm, because the state has to have norm equal to 1. So what the system state will be after the observation depends on what the output of the measurements was. So this is again a very different kind of axiom compared to what classical systems are. In classical systems, you make the measurements, and you can make the measurement such a way that after the measurement, system state is not disturbed. And so this is the main difference between quantum systems and the classical systems. Now, if we represent the outcome or output of measurement from operators mm that we have given, the output is going to be, if we represent that by x, its value is going to be m. Probability of that is equal to pm, as we have stated in the last slide. So the observation output or the system output after the measurements can be described by this random variable, which has this distribution. The expected value of the random variable can, of course, be computed by summation mpm, and its variance is denoted by delta of phi, which, of course, again, we can compute from this quantity. Example, we can start with a Hermitian operator on the Hilbert space H. The dimension of the Hilbert space is D, which is some finite number because we are considering only finite state spaces. Given M, Hermitian operator, it will have real eigenvalues lambda I and orthonormal eigenvectors corresponding to lambda I is denoted by EI. Since M is Hermitian, it's a mathematical property of such operators that the corresponding orthonormal eigenvectors form the basis of the Hilbert space H. And therefore, we can decompose M in this form. Sigma I is equal to 1 to D, lambda I, EI, E. So this is the adjoint of this operator. So which is basically taking the transpose and then taking the complex conjugate of the components. In this decomposition, we denote each one of these operators by mi. Then we can show that sigma I equal to 1 to D, mi star, mi is equal to I. This is the requirement that we have if we want to use a system of operators for measurement. So therefore, we can, starting with M as a Hermitian operator on the Hilbert space, we can define MIs which satisfy this, and we can make measurements corresponding to these MI for the quantum system. So when we talk about, so if we are given an any Hermitian operator, we can talk about taking measurements with respect to that of the quantum system, that will be understood in this form. We will be making measurements with respect to the system of Hermitian operators, Mi, given by this. If the system is in state phi, the measurement output I, which corresponding to the ith Mi, has the probability given by Pi is equal to inner product of phi, Mi star, Mi phi, as the axiom states. If the phi state at the time of measurement is one of the eigenvalues, Ej, of this system M, then from this we can say that Pj is equal to 1, J corresponding to this, and Pi is equal to 0 for any other I not equal to 0 and not equal to J. This means if in the state in which you make measurement with respect to this system of operators, then the output with probability 1 will be equal to J. And after that, the system stays in the same system state Ej, as you can verify from the axiom statement. A particular example of this is one qubit system. In one qubit system, the Hilbert space is C2, and it has bases 0 and 1 vectors, where 0 is 1, 0 and 0, 1. So these form orthonormal bases in C2, and we can take that these are standard bases that when we are considering a qubit one qubit state. Corresponding to these bases, we can define M naught as 0, 0 operator. Its matrix is, as you can straight away check from here, is 1, 0, 0, 0. M1 is I complex conjugate. This matrix is 0, 0, 0, 1. Now we can check that these M0 and M1 satisfy this. M0 star, M0 plus M1 star, M1 is equal to I. So therefore, this system of one qubit, we can take these as the basis and M0 and M1 as the operator to make measurement against. So now you consider as qubit, general qubit state phi in one qubit system, which will be a superposition of 0 and 1, represented as A0 plus B1. A and B are complex numbers satisfying this. If you take this qubit state and make measurements with respect to M0 and M1 we have just defined, then probability of output 0 corresponding to this, probability of output 0 corresponding to this, probability of output is 1. So this is given by inner product phi, M0 star, M0 phi, and that turns out to be equal to mod of A square. Similarly, probability of output 1 is mod of B square. Heisenberg uncertainty principle. This is a very famous uncertainty principle in quantum mechanics, and this is very unlike the classical systems. And this historically came up pretty much in the beginning of the origin of quantum mechanics in early 1920s and given by Heisenberg, one of the founders of quantum mechanics. In this, suppose you take two Hermitian operators C and D on the system state. Now remember, corresponding each of the Hermitian operators, I can make measurements that depend. For example, if I make measurements with respect to C, then the Mi will be corresponding to the eigenvectors corresponding to C. Similarly, for D, there will be measurements made with respect to the eigenvectors corresponding to D. Now, define commutators this for C and D in this form, which is CD minus DC. If CD is equal to 0, that means this quantity is 0, then CD is equal to DC, and therefore the two operators commute with each other. Heisenberg uncertainty principle says if we make measurements of this system state with respect to the Hermitian operator C, that means corresponding to its eigenvectors, then the measurements, the variance of the measurements, which is denoted by delta C phi square, this is the variance when we make measurements with respect to C. This is the variance which make with respect to operator D. And this inequality in that case is satisfied that the product 4 into product of the variances in measurements with respect to C and D is lower bounded by this quantity. If CD is 0, that means C and D commute, then this lower bound becomes 0. And therefore, this allows the variance with respect to C and the variance with respect to D to be equal to 0. If this quantity is greater than 0, then both of these variances cannot be 0. That means the variance, the measurement quantities will be random. So this principle says that if C and D, the commutation of C and D is equal to 0, then it is possible in some quantum state phi, if we take the measurements with respect to C or we take the measurements with respect to D, their variances will become equal to 0. It is possible because this is a lower bound. And even if it is 0, these quantities may not be 0. But for some values of phi, this system state, they can become 0, which means the perfect knowledge of the state will be available after measurement if we make measurement with respect to C or with respect to D in that state. Specific example of Heisenberg uncertainty principle. Again, we take one qubit system that is having Hilbert space as equal to C2. Bases are 0 and 1. And volume matrices that we have given earlier, I is equal to this identity matrix, this is NOT gate, and this is Y and Z gates with the corresponding matrices. If you take commutator of X and Y, which is equal to XY minus YX, you can do the computations here and see that it will be equal to 2IZ. Z, this quantity, I is equal to square root of minus 1. And this quantity is not equal to 0. That means X, Y do not commute. In that case, the lower bound by the Heisenberg uncertainty principle, if we make measurements on phi with respect to the X, or we make measurements with respect to Y, then the corresponding variances cannot become equal either in the case of measurement with respect to X or in case of measurement with respect to Y. For example, if we take phi to be 0 state, then this quantity come out to be equal to 1. So variance is 4 into variance with respect to X measurement, into variance with respect to Y measurement will be lower bounded by 1. Fourth axiom. And this will complete the axioms that are needed for the quantum systems. This is about the composite quantum system. We have said a quantum system will have a corresponding Hilbert space, or in our case, finite dimensional vector space with field C. And we denoted the Hilbert space by H. Suppose a quantum system is made up of two quantum systems, subsystems. One subsystem has Hilbert space HA, the other has HB. And this has dimension N1 and HB has dimension N2. Then this composite system made up of these two quantum systems has the state space given by HA tensored with HB. And as we have seen in the last video, the dimension of the overall system is N1 into N2. Again, this is in contrast to the classical systems, because in classical systems, if the system is made up of two parts with the corresponding state space A and B with dimension n1 and n2. Then the composite system made up of these two subsystems has the dimension of n1 plus n2. But for the quantum case, the composite system has a dimension n1 into n2, and its state space is the tensor product of this, while in the classical case, it will be the direct sum of the vector spaces corresponding to two subsystems. Now, this is for quantum system made of two parts. In general, if it has n components, then the quantum system of the composite system is made up of the tensor product of all the n quantum subsystems. Example again, now consider two-qubit system. We have studied the one-qubit system, which has state space of C2 for two-qubit systems. Now the state space will be C2 tensored with C2. And the basis for this is, like, basis for each one of them is 0, 1. So basis of these two is 0, 0, 0, 1, 1, 0, 1, 1. A general state in the two-qubit system phi will be a linear combination of these four basis components, A1, 0, 0 plus A2, 0, 1 plus A3, 1, 0 plus A4, 1, 1, with the condition that all these A1, A2, A3, A4, these are complex numbers satisfying this constraint. In the two-qubit system, we can consider, like a linear combination of this, as state phi given by 1 by square root of 2, 0, 0 plus 1 by square root of 2, 1, 1. So you can verify that this satisfies these constraints. This is an interesting quantum state in the two-qubit system because it is an example of entangled state. What are entangled states? Entangled states are the states in this overall system of tensor product of these two components, where the overall system state cannot be represented as the tensor of state in the first qubit and of the state in the second qubit. So one can verify this cannot be written as the tensor product of the states of the two qubit systems. This again is a special, unique property of quantum systems, and it does not hold for the classical systems. And we'll see later on that such entangled states, the unique property here, do give very powerful extra properties to the quantum systems. With this, we end our today's video where we have explained the axioms of the quantum systems. And in the next video, we will start with this and start describing about the quantum gates corresponding to the classical gates. Thank you very much.